everyone, I'm William Pierce from Obeo. With Ariane Moy from TNO ESI, we are going to show you how to simulate your systems using POOSL. POOSL, which stands for Parallel Object-Oriented Specification Language, is a new project proposal at the Eclipse Foundation. It offers a general-purpose method for describing and simulating systems architectures for the early evaluation of key structural and behavioral concepts, requirements, and performance. The POOSL tooling has been developed on top of several Eclipse technologies, modeling ones like EMF, Xtext, Sirius, and the Eclipse debug framework as well. This lightweight modeling and simulation approach shortens the development time of complex high-tech systems by providing fast insights into requirements and early design decisions, thereby reducing the risk of expensive iteration during design, integration, and testing. POOSL was originally developed at Eindhoven University of Technology, was adopted by ESI TNO as a standard modeling and analysis tool. It was successfully used in the high-tech industry. It is currently industrialized and open-sourced at the Eclipse Foundation by Obeo. First, let's take a look at the product in situation. This screenshot shows an overview of the main POOSL features. On the bottom left, you can see the textual syntax of POOSL, the presented model being a simple producer-consumer pattern. The textual form allows to accurately define all the simulation components and their behavior. On the right of it, a diagram representation of the same model, which gives a better view of the tested model structure. At the time of the screenshot, the model is being debugged. So you can see on the top of the classic debug trees and variable views. Finally, the bottom right view is a dynamic sequence diagram showing the interaction between the POOSL model processes in real time during a debug session. Now that you have a glimpse of POOSL, we are going to explain how it can provide early system validation, demonstrate it through an example. After the demonstration, we're going to explain the language and features. Finally, we're going to give information about our future plans for the project. Now, Ariane will show you and explain the origin of POOSL.
Thank you, William. Yes, thanks for this introduction. I'm glad that I have the opportunity to explain something on the background of POOSL, where it came from and also its purpose. And as you can see on the slide, there's already kind of the summary. It's all about early system validation using lightweight modeling and simulation. But let's start at where this comes from in terms of where do we apply these things. So POOSL was developed for the application domain of what we call concurrent hardware-software systems. And what can you think of? What should you think of? Now, first category would be things related to electronic systems. So people talk about system on a chip, multiprocessor architectures, and digital electronic circuits and systems. And what you see here is that there's always a lot to do about the computation platform, so really how the chip is organized. But also, there's a lot to do about the functionality and how you provide that, for example, using software. So it's this combination. You see the platform and the functionality. Another application would be what people call cyber-physical systems, or these days sometimes people call it embedded systems or high-tech systems. And these are systems that can range from very small, like the size of a watch, to very huge systems like big industrial copiers or big industrial systems that are used in operating theaters from hospitals. So really big systems. And if you look at what's very characteristic for these systems is that there is again a combination of components. Partially there are really physical hardware and mechanical components, and partially there are a lot of software components with valuable functionality. And what you see over here is that these components really have to interact closely with each other. So they are independent components, but they really need to interact. And that's typically the place where it becomes very interesting. If you look at the development of this type of systems, then we like to look especially at the very early phases of their development. And that's typically the phase where you see that people have an idea what they would like to develop, roughly the kind of functionality, but still the requirements are also very imprecise, incomplete. There's still a lot to be decided. And especially in these early phases, we see that many decisions are taken, especially architectural decisions. Now, if you look at what kind of decisions are these, well, first of all, that's kind of the total decomposition of the system, from the system into smaller components. But if you split the thing in smaller components, you also have to think about what these components are going to do. So you talk about distribution of responsibility and functionality over all the components. And if you've managed to do that, then you still have to decide how they are going to interact with each other. It's not just dividing, it's also they have to interact with each other. So we see a lot of these decisions are being taken. And well, if the big risk over there is if you make suboptimal decisions or decisions that are not completely clear, then later on in the development process, these decisions may cause big problems. And then what I mean by later on, some of these problems can only become visible during design or integration or even testing. And if you have to correct anything during these phases, then it's very time-consuming and expensive to do so. So the whole thing that we have in this phase is there's a lot of things are imprecise. We make important decisions, and we want to be as sure as possible that we're making good decisions. And that brings us to the goal of the POOSL tools. That's in the end, we want to shorten development time by providing means for early system validation. So you get early feedback on whatever you're designing. So what kind of things could we validate in this particular stage? And here I have a couple of examples. So the couple of properties that need early validation. Well, first of all, they're related to the functional requirements. Maybe the question is, do we really understand what the customer wants? And do you really understand all the possible feature interactions between all the nice features the customer would like to have? The second category is more on decomposition, the architectural decomposition in smaller blocks. So do we really understand the behavior of the components and the functionality of the components, and especially how they will work together in critical use cases? So not only the happy flow. And the third category is about performance indicators, really KPIs. For many of these systems, it's very important that you have a good estimate of what will be the throughput of the system, or the latency, or even resource usage. So these are three categories of properties that really need early validation. If you look at what is common practice at the moment in industry to deal with these kind of questions, then we see a lot of what we call plain drawing tools. In early architecting, there are a lot of these diagramming tools, very easy to use, but also very informal. I mean, it's in a way, it's very easy to agree on diagrams, but it could also mean that maybe it's too easy to think that you agree. I mean, it's very easy to have a confusion over there. A second category of things that we see is what we call elementary calculations, kind of back of the envelope, to make a first estimate of what will be the throughput of your system. But we will quickly see that this is getting too imprecise, and you would like to have something that's a bit more detailed. And then the third step that we see is that many industries quickly go to physical or virtual prototypes to really, okay, let's make the whole thing and see how it works and what are the good decisions. But we think that in this phase, this is actually too detailed, and you would like to have something that is much more lightweight. And that brings us again to POOSL. We say POOSL is meant for lightweight modeling and simulation. So really meant for these early phases. We work on executable models, so that are models that not just give a formalization, but they can also actually be simulated and they become alive. But still, you want to abstract from as many details as possible, because there's still so many unclarities and we are in this early phase. And what we see very often is that we try to combine such models also with domain visualizations to really bridge the gap to the customer. And the whole goal there is, well, provide fast insights in your requirements, your early design decisions, with the ultimate goal of reducing the risk of expensive iterations during the later phases like design, integration, and testing. Well, I can imagine that you now think that there's been a lot of words, so what is this really about? And that brings us to the second part of this presentation, where we like to give you a short demonstration of how we would do this with POOSL. And for that, we take the example of a so-called in-flight entertainment system, where you will actually see that there are different use cases. I mean, on the one hand, the passenger just wants to watch nice videos. On the other hand, the flight crew sometimes have to do important announcements. So we will take this as an example and explain you exactly the steps that I was explaining before using POOSL. So let's have a look at this video.
Let's look at what this means for an in-flight entertainment system, which probably looks familiar to you. Such a system is also used as an example by the model-based systems engineering tool Capella, which gives a glimpse into how this may look on the inside. Let's focus in particular on the functional chain for broadcasting an audio announcement from the flight crew to the passengers. The splitting points immediately catch the attention with respect to synchronization.
We have created a lightweight simulation model using POOSL. This is a tool for system modeling and discrete event simulation that has been developed by AZ together with Eindhoven University of Technology. At the top level, we model the in-flight entertainment system, surrounded by a passenger to the left and the aircraft to the right. The in-flight entertainment system is composed of two interacting components, like the seat TV, which can again be decomposed. Finally, the behavior of components like the audio-video player is described using built-in primitives for parallelism, synchronous communication, and discrete time. The idea is to model just enough behavior to be able to simulate the critical functionality. To analyze the audio announcement, we also need to consider interacting features, such as a video being watched.
How can you use such a model for system validation?
To validate the functional requirements, we use high-speed simulation. By monitoring the passenger, we see the videos interleaved with audio announcements. In particular, we can discuss whether the video should be paused or suppressed during the audio announcement, which is a choice that may have an impact on the proposed system architecture.
In the simulation output, I see that the video ends later than the expected end time. So you have decided that the video must be paused.
You may also have noticed that the simulation suddenly stops. To diagnose what's happening, we use interactive simulation. You may recognize many familiar debugging features to control and inspect the simulation. In addition, you can see built-in features such as the communication diagram to the left and the sequence diagram to the right. Again, the simulation suddenly deadlocks, but now you can analyze the sequence diagram. In this way, you can discover that certain components may become out of sync in a scenario in which announcements follow each other rapidly.
Hello, ladies and gentlemen. This is your captain speaking. We'll be landing in the airport in just a few minutes. Ladies and gentlemen, as we start our descent.
Your analysis clearly indicates that this synchronization aspect needs to receive attention.
Finally, we have extended our simulation model to estimate the broadcast latency, all the way from the flight crew to the passenger. This latency is impacted by the architectural decomposition and the component synchronization, and can be evaluated using high-speed simulation. In addition, Gantt charts can be used to visualize and analyze the timing. For example, the activity diagrams show the interrupted videos, and the research diagram shows the flow of announcements through the system.
These simulation models do not require implementation details and hence can be made in early phases of system development.
Indeed. So that was the video.
Let's look at what this means. Let's look at.
Interesting. Yes. So I think in this video, you saw exactly the three kind of categories that I mentioned before and how they could be, or these kind of categories of questions to be validated and how they could be addressed with POOSL. But I can also imagine that this was actually going very quick in terms of what is POOSL really offering. And for that, I like to go through the language and the tool features step by step. So I will start with the first level, hierarchical decomposition. How do you model such a system decomposition? Then we dive deeper into, okay, the process behavior, discrete time process behavior. And then as a third step, we go to the object-oriented data structures. And then as a last one, number 4, will be the tool features. And for that, by that time, we'll go to William. But let me first continue with the language features. So the first language feature is all about hierarchical decomposition. So coming from a big system to these smaller components. And here at the bottom, you see an example of what we call a cluster, which is one of the units for the hierarchy. And here you see, for example, the models that the top level system consists of a CTV plus some kind of a server. And you can do that actually in multiple steps. So at the bottom, you see there is both a graphical representation and a textual representation, and these are synchronized. And sometimes one notation is nicer, and another one is the other is nicer. So the first concept that you see here is what we call a port. These are the yellow blocks on the border of the system, and these are really for external communication. That can be communication with another cluster from your POOSL model. But it can also be external in the sense of connecting to a file or connecting to a TCP/IP socket. So in this way, you could do co-simulation with maybe a visualization tool. If you look inside the cluster, then you will see there are so-called instances, like in this case, a CTV. And each instance, again, has some ports. These are the blue blocks. And these are the internal connectors. And finally, we draw channels between pairs of ports, or even more ports, to indicate that they can communicate messages with each other. So that's kind of the basic mechanism that we have for decompositions. You have instances, you have ports. You do that in the multiple steps, and at the lowest level, we don't have clusters anymore, but we have so-called processes. And these processes, the idea is there we're going to sketch a little bit the behavior of this of the process, and we try to again abstract from as much detail as possible, but we have to specify it here. So a process again has some ports, which are the external connectors for communication. But in this case, we go one step further because we also specify the messages. Because for every port, there can be multiple messages that can be sent or received over this port. And these messages can also have certain parameter types to model data transmission. In addition, processes have variables. To be more precise, they are protected class variables. And there's a so-called initial method call. And that's the thing that really starts the behavior, because the processes have behavior from themselves. And we have to say where it all starts. If you continue looking at a process, then you specify so-called methods. And here at the right-hand side, you can see 3 examples of methods, also things from the video. And inside these methods, you will probably see a lot of statements that you recognize from many of the languages that you may be familiar with, programming languages. But there are also a couple of statements that may be a bit more special, and I'd like to give some attention to these. So first of all, there are messages that are for sending and receiving messages, and we use exclamation marks and question marks for that. We also have a built-in notion for parallelism. So you can really specify, okay, these fragments, do them in parallel, and that's just using the keywords part and wrap. It's not more complicated than that. Also for choice, non-deterministic choice, what we see very often that we want to model processes that wait for multiple messages and then just see, okay, which message is available. Okay, and then we decide to handle that particular message. So this gives rise to choice, non-deterministic choice. I already mentioned that process behavior is also about discrete time. So there is a notion of time. And we have a delay statement, which can indicate, okay, the process has to wait a certain number of time units before it can continue. And we use, for example, time to indicate also, yeah, okay, there is some internal processing that we don't care about at the moment, but we just want to indicate it takes some time. And then we can model it and take it into account for the performance analysis. The last 2 statements I like to mention are the abort and the interrupt. They are a bit related. The idea with an abort is that you specify a certain section of statements, a certain behavior to be executed. But the moment that something happens, for example, a certain event occurs, maybe time, a message, a user input, then you immediately want to abort the original behavior. And as a variant, you have the interrupt, where we say you have certain behavior is being executed, but the moment that a certain event or time trigger happens, you want to interrupt the behavior, handle the event, and then continue where you stopped. And this last one is something you can see in the top right. We use this, for example, for the video player. Play the video, but there can be an interrupt because of the flight crew doing an announcement. And once that is done, you actually want to continue playing the videos. So that to give you an overview of special statements. In the end, quite often you also want to have some data being modeled. Well, we have object-oriented data structures. So a single inheritance, again, variables. But here all the methods are really atomic operations. So you don't look at the interleavings anymore. In addition, we have a built-in API with all kinds of predefined data classes. So in many cases, you can just reuse them. Built-in classes range from booleans, all kinds of numbers, string representations, but also external I/O. So via console, via files, via the socket, random generators, and some data collection structures. So I think this is the right moment to hand over to William to continue with the tool features. So William, can you take over?
Yes, thanks, Ariane. So the POOSL Eclipse tooling provides all the necessary features to edit, run, and analyze simulations. A POOSL model can be viewed and edited as text with the help of the Content Assist. File importing allows factorization of common uses in libraries. Several graphical editors are available, giving a better overview of model structure. POOSL models can be validated, warning and quick fix help making them correct. A simulation can be debugged with the help of breakpoints and a dedicated sequence diagram view. It can also be directly launched in a high-performance fashion from IDE or command line in a batch purpose, for instance. Now, we are going to end this presentation by showing the envisioned next steps for the POOSL project. Obeo is currently working on the POOSL source code in order to improve reliability, maintainability, and allow the development of new features. The code has been refactored in order to comply with Eclipse naming conventions. The release engineering system has been reworked as for integration tests. Then we were able to improve the basic code quality aspects and fix a few bugs. A new example wizard has been added, and diagrams are being redesigned to improve ergonomy and readability. In parallel, Obeo provides a professional bundle which offers a ready-to-go version of POOSL, better suited for users that are not familiarized with Eclipse. Finally, for the next steps, Obeo plans to work on scalability aspects, improve the handling of large models. Then we envision several possible integrations with other frameworks. Eclipse Capella, a full system engineering method and IDE. Eclipse Comma Suite, a modeling and analysis tool for component interfaces. And Eclipse Trace for CPS, which can provide a way to analyze POOSL simulation results. You can try POOSL right now. The source code is available on GitHub, and you will find installation instructions on the website. An Eclipse proposal is in progress that you can consult on the link. So thanks for your attention. Thanks, Ariane, and we will be available now if you have any questions. Okay, so first question. How does POOSL relate to the GMOC initiative? Was some parts principles of GMOC reused? Was POOSL a reboot with more recent technologies? Does it have different purposes? So those are two complete different initiatives. POOSL does not use a serious animator like Gmok, and POOSL relies only on a serious desktop. What is the relationship between POOSL and Capella? There is no relationship yet, but we have in our roadmap to study how to integrate POOSL with Capella. Is the simulator implemented specifically for POOSL, or do you reuse some semantics for other projects in the area of embedded real-time systems? Example, Ptolemy.
No, as far as I can take that one.
Okay.
No, the simulator is specifically implemented for POOSL. There is no reuse from other projects in this case. Okay. There's still room for a few questions. We have about 3 minutes left. Well, coming back to the first question, maybe it's good to indicate that POOSL was developed about between 15 and 20 years ago, so it is not based or rooted in rather recent developments.
Okay, so if there is no other question, we can finish here. Thanks you all for your attention and your questions.
Thank you very much. Bye-bye.
Bye.